Hello, here Roger, Adrian, and Betty from Spain. I hope you enjoy our presentation. Today, we're going to show you a new form of doing and understanding synthetic biology. And I'm happy to say that you're going to see the future of biological printing. Let's start. Printing history is very long in time. It started in the 9th century with types, typography, and with the diamond sutra. Then, between the 15th century and the 16th century, Johannes Gutenberg developed what we call the modern printing. And today what we have is the digital printing, where you can do a design in the computer and you can print it. It doesn't matter how much knowledge do you have. Lab history is similar. From the most basic lab, like the medicine lab, such as the Ramonic Hard Lab, to the current labs that we have today, it has evolved exponentially. But how is the future like regarding laboratories and printers? I have the pleasure of presenting you Iteria. Iteria is a simple device that automates and democratizes synthetic biology by making it low cost, time-saving, and accessible. Let's not lie. Successful iGEM teams are formed by multidisciplinary members. That's why our team is formed by engineers, biotechnologists, and designers. To broaden our horizon of knowledge and make something bigger, something greater. Iteria is a conjunction of several disciplines. Do you imagine a printer without its control software? Or without its ink? And without the physical part or the user's needs included in the design? Of course not. So let's use it. Now, Adrian will continue. Betty, sorry.
Thank you, Roger. Hi, iGEM. Well, continuing with the symbol of a printer, Iteria has 3 parts. An entry system, similar to a cartridge, a printed circuit board, or PCB, where the biological reaction happens, and finally, the output tray, where the transformed bacteria grow and can be measured. First, we need to introduce the consumables or bioink in the printing area. For that, we have created this carousel-based system that can be rotated using a stepper motor. There, the pipette tips with the bioinks are placed in each position. Then, a solenoid is activated that lowers a needle, and by means of a peristaltic pump, the droplet with the bioink falls to the printing surface. But what is bioink? In Iteria, bioink includes 3 components. The basic parts, the competent bacteria, and finally, the enzymes necessary for the assembly reaction. Each of them are contained within the pipette tips. Our team, for providing the DNA pieces, has developed a complete basic part collection that includes 8 promoters, 5 RBSs, 13 CDSs, and finally 1 transcriptional terminator. Now, for making the construction, we need an assembly standard easy to automate, a way to move and mix the components, and to reach the adequate reaction conditions. So, working together, engineers and biotechnologists, we got the solution. The assembly standard chosen is Golden Gate. We choose it because we can make a construction in a single step, in a single job. And also, because it's a highly robust method. That's why our basic part collection is compatible with BioBricks and also with this assembly standard. Recalling the hardware, we were talking about the droplets with the biobeam falling on the printing surface. But what happens once there? Now, we need to move and mix the different components. Here is where magic begins. We use the digital microfluidics technology that moves droplets on surfaces by using the electroweighting effect. But what is this? The electroweighting effect consists on altering the hydrophobic properties of a surface by applying voltages. The surface is nothing more than a printed circuit board or PCB covered with a very hydrophobic material. After several testings and PCBs, we design a surface that allows such movement. Now, we have the droplets moving. So we need to solve the requirement of different temperature cycles. For that, instead of using a thermocycler, we have created two zones at a constant and different temperature where the reaction droplet moves. But how? How are we going to get it? Using two components, a resistance and a peltier. The first one will increase the surface temperature up to 37 degrees. And the second one will extract the heat, decreasing the surface temperature to 16 degrees. As we can see here, making a reaction with these two temperature zones is possible. While the assembly reaction is taking place, the competent bacteria are resting in a separated area at 4 degrees. Once the assembly is complete, the reaction droplet merges with that with the competent bacteria. Now, the bacteria are ready to be transformed. The idea is to electroporate them while they're being transported to the output tray. As proof of concept, we electroporate the bacteria using the electroporator developed by the high-pitch VALENCIA 2016 iGEM team. And we got these good results. Now, let's see what happens now. The bacteria are ready to grow and be incubated in our output tray. But this is not the most important, because we can take all the optical density and fluorescence measurements. Let's see the results of our sensors. On the left, we can see the calibrate of the measurements of our growing bacteria. And on the right, we can see the calibration curve of our fluorescence sensor. In the x-axis, we have the measurements of our sensor. And in the y-axis, we have the molecules of equivalent fluorescein per cell. Now, Adrian is going to explain the software.
Thank you, Betty. So, do you think that you can use a printer without any software? Of course not. Iteria is controlled by two Arduinos in parallel. These Arduinos are connected with a Raspberry Pi. The Raspberry Pi sends the instructions to the Arduinos and receives the data from the measurements in Iteria. The user controls the Raspberry Pi through a very intuitive software. The software has three principal functionalities. Inventory, where you can check the available bioinks. Recipes, with pre-designed composite parts. A new job, where you can design your own composite parts. In the inventory, you can recharge the bioink by clicking on the cartridge. You can also change the part in that position. In the recipes, you can select and print one of our pre-designed composite parts. You can select it by selecting a registry number or a short description. In your job, you can design your own composite part if you know what you are doing. You can design it by selecting a promoter, an RBS, a CDS, and a terminator. But this is not all. The main objective of our software is to allow the future development of Iteria. That's why we implemented all software methods in an application program interface. One functionality of our software is to predict the behavior of a composite part before printing. To do this, we did two things. We did a modeling simulation tool, and we characterized all our basic parts. The simulation tools combines the characteristics of each basic part selected to obtain quantitative results. But how did we get the characteristics of the basic parts? First, we did a mathematical model, and at the same time, we did a measure of the composite part constructed in the lab. Then we combine the results of the lab measurement and of the modeling in an optimization process in order to obtain the model parameters that defines the part. Here is an example of an optimization process where we obtained the translation rate for 3 different RBSs. Now, Roger is going to continue.
Thank you, Adrian. Well, this year we wanted human practices to be a part of our applications. Let's remember that one of the main objectives of Iteria is to make scientific biology accessible. So next we're going to answer 3 questions. How we have done a device which is made with the user and not for the user, how we have implemented safety in our device, and how we have joined public engagement with integrated practices. For our public engagement activity, we took Iteria to the Mustang Art Gallery, where students and teachers were waiting us to see what we had done. We showed them Iteria and we explained them Iteria, and they had the chance to do bioartistic art with the products of Iteria, which we call the printome. Well, the results were amazing. There, we gathered them and we invited them to make suggestions about Iteria. That feedback, we included it in the Kano model. Remember this word, because you're going to use it in future iGEM projects, Kano model. What is Kano model? Kano model is a methodology that helps you to include feedback in your device. In simple words, it classifies the user's necessities according to how much satisfaction they include to your device if you include them. Let's see how it works. First of all, you have to take feedback from a public engagement activity, and then you have to make a survey of paired questions. What are paired questions? Each necessity makes 2 paired questions, okay? For example, I always put the same example. If a kid says, I want Iteria to have LED lights. Okay, to have LED lights is a necessity of the user. So you would say in the first question, how do you feel if Iteria had LED lights? And in the second question, how would you feel if Iteria didn't have LED lights? So once you have the service done, you have to return it to the users that gave you the feedback. Then you have to process the results with the Kano model and obtain your conclusions. Let's see your conclusions. At the end of the process, what you have is your needs classified in 6 levels of satisfaction. From the bottom to the top, satisfaction increases. And our results were awesome. We classified 7 necessities, so you can see here. And the majority of them obtained an A, so we had to implement it. We have done it with the majority, and some of them will be implemented in the near future. But what we have done here, we have joined with the Kano model, public engagement, and integrated practices. We've made sure we don't waste time and money implementing needs that are irrelevant to users. But most important, this is documented in our wiki in a way you can build upon. So please use it. Let's go with external feedback. We did interviews with personality, with biotechnology and engineering, like for example, Ryan Fogel, which is biomedical engineering, with Ana Miriam, bioartists, Francisco Mojica, he's Spanish and he discovered CRISPR system, and with Maria Benil and Memo. Thank you. Well, new technologies create new art forms. This is especially true for art. Iteria, which can be seen in the image, is a painter that mixed computer science with art. Here at MIT, at the early 70s, now with 77 years old, he was eager to learn how Iteria can do for art. We did an interview with him, and we gave him the chance to do something with the products of Iteria. To show the world how powerful Iteria is, we tried to do one of Iturralde's impossible figures. Here is the impossible figure Iturralde did. And the next image is what we did with the products of Iteria. Amazing. Well, how we have included safety in Iteria? Well, before doing anything with Iteria, we thought about the sterilization of the PCB and the microfluidic tubes, the protection of the user, the electrophoretic use, the overheating and ventilation, and the disposable tips. All the answers were included in the design. Let's go with the collaborations. Thanks to those who collaborated with us. Thanks to the Universidad Complutense de Madrid. Thanks to the Universidad de Marburg. Thanks to the Universidad de las Fuerzas Armadas ESPE. Thanks to Harvard University. And thanks to the Imperial College. Thank you. To sum up.
No, it's not.
We have, excuse me, I haven't finished yet. Please put the last slide. Thank you. To sum up, we have done an extensive part collection. We have done an awesome hardware that you have seen in that exhibition place. We have done a model to characterize our parts. We have done an intuitive software to control Iteria. We have done an innovative methodology to include feedback in your project, and we have done several public engagements. So now, thank you, audience.